Alright, so here we are in part 2 of our rates of reaction videos. Okay, so in our summaries, let's talk about how we measure the rates of reaction. Now, this is one of those things they add into your skills, so it's quite important that you understand how we would measure different rates. Okay, so when a gas is produced, and really this is as much detail as you need, there are two ways we can measure rate. Number one, okay, so these two methods are for measuring the volume of the gas produced. Okay, so here we're going to measure the volume directly, either by using a gas syringe, which just fills, or here they've used a burette. You can also use a measuring cylinder. As long as it's upside down, we fill it with water, and we use the downward displacement of water. So the gas bubbles up, the water comes down, we're all happy, we can measure the volume. Okay, so we're measuring the volume of the gas produced. However, and these are the enclosed systems, so it makes it easier for us. However, when a gas is produced, we can also allow the gas to escape. So here we're going to be measuring the mass. Now, depending on how they give you this, they're either going to give you a table or whatever of how the mass decreases over time, or they'll just be nice and tell you how much mass is gone. So, because however the mass decreases on the scale, that's the mass of the gas that is escaped. Okay, and it's got to be a very sensitive electronic scale. All right, it can't be any other type of scale. It's got to be an electronic scale. And it really does need to be quite sensitive for you to see this. Okay, either one is fine. These are for how we measure a gas. Gases are easy to measure. Very, very easy to measure the rate of reaction. When a solid is produced, it's a little more difficult. So the first method is by measuring turbidity, because by solid being produced, we mean that we're forming a precipitate. In other words, ignore what that is. A precipitate means we're producing a solid that's not soluble. Okay? And that solid then is usually formed in a very, very fine powder. So what this system does, which we wouldn't really do at school, there'd be an app on the computer that really measures. So we have a light bulb, shines through here. We have a very sensitive sensor that can measure how much light is going through it. It's difficult to draw a graph from this, but you could, all right? And the laptop and the app on the laptop, or whatever the case may be on the screen, would be able to show you look at the amount of light. So you could do something with it. The other way is by drawing a big fat black cross on a white surface and measuring till you can't see it. Now here we can't measure the rate in the sense of going, I can measure every 20 seconds and I can get some sort of reading. Basically, you can only measure with this one the speed to get to the end of the reaction. Alright, and we would use this particular method when we want to measure how different things change the effect on the rate of reaction, how fast the reaction happens. But we couldn't really do it if we wanted to be able to draw a graph from it. So it's not great. Okay, now we need to talk about the factors that affect the rate. You also at this stage need to realize that in Teams, there will be a link to a YouTube video, which is a nice analogy of what this is. Okay, it's actually a really nice little analogy. Please take your time to watch it once you've done this or before. So pause here, go watch that, then come back. Either way. So, the rate of a chemical reaction describes how quickly products are formed or how quickly reactants are used up. And they're always measured relative to time. So, the rate of reaction is affected by the nature of reactants. We will talk about it, but we can't do anything about that. The concentration of the reactants, the temperature of the system, and here we really mean initial. All right. A catalyst, and also, which should have been here, and I really should fix these, is surface area. Okay, and this is only about for solids. Concentration is for gases and solutions. Okay, so let's get going. With surface area, now here you need to listen carefully because this is going to feel a little counterintuitive. Okay, I have to look at total surface area, okay? And it only applies to solids. Please, you must read the question carefully. So this reaction is a gas, is an acid with magnesium, for example. When we have a big chunk of magnesium, only those particles on the outside can react at the beginning. So they have to react, go away before we can see the next ones. So that's the total amount, that's the surface area. When we break it up, so we go from big chunks, so here we crush it, we make it into a powder, we make it into smaller pieces, but now if I had to calculate the total surface area of all these pieces together, so all of this, the total surface area has increased. All right. Now, if I increase the total surface area, now I have lots of particles that are available. The more particles that are available, the more collisions we're going to have. And if we have more collisions, the chances are that we're going to have a greater number of effective collisions. So, if we increase, now what I need you to see as well in your notes is that I've only done these reactions from the point of view of increasing the rate of reaction. Everything is the reverse if I decrease it. Okay, so if I increase the surface area, we increase the number of particles available for reacting, which means the particles collide more frequently. There's a greater number of effective collisions per unit time. We increase the rate of reaction. If I decrease the surface area, I decrease the number of particles. They collide less frequently. There's a smaller number of effective collisions, so we decrease the rate. Those are the numbers, the words that become the opposite. So, in general, if I increase the surface area, I increase the rate. If I decrease the surface area, I decrease the rate. What about nature of reactants? Well, nothing we can do about that. The type, the strength, the number of chemical bonds, or the attraction between atoms determine the speed of the reaction that particles have to collide with and to create an effective collision. We have no control over that, okay? I cannot change the nature of the reactants. They are what they are, okay? Let's talk about concentration. Only applies to solutions and gases. When we have a low concentration, we only have few particles per unit area. When we have a high concentration, we have lots of particles per unit area. More particles we have, the more collisions we can have. So what? If we increase the concentration, we increase the number of particles. Particles collide more frequently. Greater number of effective collisions per unit time. We increase the rate. If I decrease the concentration, I decrease the number of particles. Collide less often. Smaller number of effective collisions, we decrease the rate. So, increased concentration increases rate. Decreasing concentration decreases rate. This is a very nice section. It's all the same thing over and over again. Now, if you've been paying attention, you're realizing that list we just did, I didn't include pressure. Pressure is simply a way for us to change concentration of gases. Only applies to gases. Please be careful. It's one of those things they are going to try and trick you with. So, when I lower the pressure by making a large volume, we have fewer gas particles. This is a small concentration. Okay, so we decrease in the concentration. If I make the pressure higher, it goes to a smaller volume. There's more gas particles. So this is a higher concentration. In other words, this will now work the same way as concentration does. Alright, lower pressure, smaller concentration. Higher pressure, higher concentration. So if I increase the pressure, the particles become closer together. The particles collide more frequently. There's a greater number of effective collisions per unit time, and we increase the rate of reaction. If I decrease the pressure, Particles are further apart, they collide less frequently, there's a smaller number of effective collisions, and we decrease the rate of reaction. So, increase in pressure increases rate. Decrease in pressure decreases rate. Let's talk about temperature, which we've actually done a lot, especially in part 1. Remember, temperature, and this really is a definition by the way, is a measure of the average kinetic energy of the particles. So this is now not only about making them collide more often, but making them collide with sufficient energy. So, if I increase temperature, we increase the kinetic energy, particles collide more frequently, more collisions will have sufficient energy, we have a greater number of effective collisions per unit time, we increase the rate. So, decreased temperature decreases kinetic energy, collide less frequently, less collisions have sufficient energy, smaller number of effective collisions per unit time, we decrease the rate. Very straightforward. Increasing the temperature increases the rate of the reaction, decreasing temperature decreases the rate of reaction. Okay, what does the catalyst do? Well, we use positive catalysts and they increase the rate of reaction without being chemically changed. Generally, a catalyst is actually described as being a substance that alters or changes the rate of reaction, but we only use positive catalysts at school, which increase the rate. You do get negative catalysts. Negative catalysts decrease the rate, and they would be used in industry or in a lab where the rate of reaction is too fast and it's dangerous, or they just need to slow it down for other reasons. Okay, so we do get negative catalysts. We don't use them at school. We only use positive catalysts. What do? They lower the activation energy. So more particles have sufficient energy. This is the big thing. Greater number of effective collisions per unit time, we increase the rate of reaction. There's no opposite to this. Okay, by adding a catalyst, this is what you do. All right, very straightforward. So as an example, in the following chemical reaction, state 4 ways in which the rate of reaction can be increased. Please, you need to be specific. We have a solid and we have an aqueous solution, so we can talk about surface area and we can talk about concentration. So the first one, increase the surface area of the zinc. We can also increase the concentration of the HCl. Then we can say increase the temperature. That should be the initial temperature. Please be specific. And we could use a catalyst if necessary. In the following, state only 3 ways. Now you need to be careful. Okay, I've said in the first one, increase pressure. Increasing pressure changes concentration. You can't now say change the concentration, increase the concentration of the H2 and the I2 as well, because it's the same thing. I can say increase the initial temperature, and I can say use a catalyst. Please be careful with this one. Okay. Last activity you need to do here is activity 7 on page 219. Please go and look at the memo in Teams, and we're done with rates. Hope you made sense.